All right, so today we're going to look at lesson 54, rotational inertia. So hopefully after this lesson you will understand rotational inertia. Several months ago we talked about Newton's first law, and it's an observation that every object is content with its present velocity and it resists a change in its velocity. Remember, an object in motion is going to continue at motion until something acts on it. If you push a cart across the room, the reason it's going to slow down is because of friction. If we didn't have friction, it would just keep on going forever and ever. It would be content at that velocity, and it's going to resist a change in velocity. Okay, that was dealing with his first law. The resistance to a change in velocity is called inertia. Some of y'all may have heard that word actually in another science class, or just heard it around. Someone has mentioned it before. But inertia is the resistance to change in a velocity. We have two kinds of velocity. We have talked about both of them this year. We've got linear velocity and we have angular velocity. Linear velocity, you're going in a line. Angular velocity, you're going around a circle. You're turning. A car that is going straight would be linear velocity. But if you are on like a NASCAR driver, they are going to have angular velocity because they're constantly going to be turning. If any of y'all ever run around the track at the school, around the football field, it's easy to run on those two sides that are completely straight. You can go really, really fast. But once you go around that curve, you've got to turn. And so your velocity is called an angular velocity because you're going at an angle. And so you may have to slow down a little bit to be able to go around that because you've got to work a little bit harder because you're going at an angle. So those are the differences. On those two straight sides of your track, I'll draw the track for you. You've got your track here, this part here, and here you would be doing the linear velocity, and this part here and here is where you would have the angular velocity, in case you've forgotten what those two are. So looking here on the left, that would be a linear velocity. We're just pushing, and we would just have mass times acceleration. That would give it a linear acceleration. And so that is using Newton's second law, F equals ma. Over on the right, we would have torque to turn something. We talked about torque. Remember when we had the wrench problems? That was a torque question. For angular acceleration, that's that little symbol right here. No, that's not angular. Yeah, that is angular acceleration. Angular velocity is that little symbol. This is your angular acceleration. And to find your torque, you do mass times the radius squared times your angular acceleration. And this r is the distance from the point of rotation. So the r is from here to here. Because if you made a circle, if your mass turned around that center, it would be the radius of that circle. If you are interested in the proof of that formula, they prove it in the book at the end of the lesson on page 374 and 375. So if you're interested in looking a little bit more in detail at that formula, that's where you can look. So we're going to look at example 54.1. We have a point mass of 2 kilograms is attached to the end of a massless rod that's 3 meters long. And the rod is pinned so that it is free to rotate about its other end. What torque is required to give the mass an angular acceleration of 6 radians per second squared? So we're going to use our formula. We have m r squared and then times our acceleration, our angular acceleration. So our mass is the 2 kilogram mass. Our radius is 3. That's the distance from the center. So we do 3 squared. And then our angular acceleration is 6. And so we are looking for our torque. And so if you multiply those together, you're gonna get 108. And the units on torque is a Newton meter. However, we need to do our sig figs. We had one sig fig, and so 108 with sig figs is going to go to 100 with no bars over your 0, because we only want to have this 1 as our only significant digit. And then Newton meters, and so 100 Newton meters would be your answer. Okay, that's the unit of torque, just a Newton meter. So that may be something you want to put on your note card, that units for torque are Newton meters. Okay, let's look at the next example. 3-point masses are affixed to the surface of a massless table that can turn without friction about its center. The masses M1, M2, and M3 are 1, 2, and 3 respectively. The lengths R1, R2, R3 are 0.1, 0.2, and 0.3 respectively. What torque is required to give the system an angular acceleration of 4 radians per second about the center? So on this one, the torque that's going to be required is going to be the total of the torques required to move each of the individual masses. So you're basically going to have to use your formula 3 times. Okay? So we're going to use our torque equals mr squared times your angular acceleration. And that's going to be for the mass 1. And then we're going to do torque equals mr squared angular acceleration for the second mass. And then torque for the third mass, mr squared and your angular acceleration. And you have to do all 3 of them because we have 3 separate masses that we've got to turn. So for the first one, the mass is 1 and the radius is 0.1 and the angular acceleration is 4. And so if you multiply that out, you're going to get 0.04. For the second one, the mass is 2, the radius is 0.2, and again the angular is 4. So if you multiply those out, 0.32. And then the last one, the mass is 3, the radius is 0.3. I forgot a squared over here. I'm sorry. And then your angular is 4. And so if you multiply those out, you'll get 1.08. And so that would be the torque for the first object, and the second one, and the third one. And so if you add those 3 together, you're going to get 1.44. And we have 2 significant digits in our problem, so that would just be 1.4. And then again, the units on torque are Newton meters. So that would be the torque that you would have to give to the system to get your angular acceleration. Okay? Looking at one more example. A 4 kilogram mass and a 7 kilogram mass are mounted on the ends of a light rod as shown. The rod is pinned so it is free to rotate about its center point. A torque of 150 Newton meters is applied. What will be the angular acceleration? So we're going to use our formula. Alright, so on this one you're going to have to use the formula, but it's going to be a little bit different because we have a total torque of 150, they tell us. Since they give us the total torque, we can go ahead and say one formula. The total torque is your M1 R1 and then the M2 R2. And so that would be your formula. This is the torque from the first mass, and this is the torque from the other mass. And so they tell us the total torque is 150. The M1 is 4. And the radius from the center is 3 for it. And we are looking for the angular acceleration. And then for the other one, the M2 is 7. The radius for it is 3 as well. And then we're looking for the angular acceleration. So we have 150. This is 63. plus 36. Actually, I have those backwards, I believe. Yeah. And so if you add those together, you have 150 equals 99 angular acceleration. And so if you divide, your angular acceleration is 1.5 radians per second squared. And so that's how you would do that one. Okay, so again, if you want to look at a proof for that formula, check in the book on 374 and 375. Your homework is 1 through 20 and the curveball questions, so make sure y'all do those tonight so that we can go over any questions you have tomorrow.